Okay, so let's discuss about the next very important concept called the Gibbs free energy. So Gibbs free energy is another variable that we are defining in here. Like we defined enthalpy as E plus PV previously. We then defined entropy, that was Q reversible by temperature. In a similar way, we are now defining Gibbs free energy as another term in thermodynamics, and that is defined as E plus PV minus Ts. Okay, so E is the internal energy, pressure, volume, temperature, and the entropy. So this G is the Gibbs free energy. So this is how we define it. Now, we know that E plus PV is equal to H. So now Gibbs free energy is generally commonly written as H minus Ts. Okay. Now Gibbs free energy is the amount of available energy in a process. Okay. Now Gibbs free energy is also an extensive variable. We'll discuss what this available energy means in a while. But for now, let's understand how what are the different characteristics of the Gibbs free energy are. So Gibbs free energy is, again, like it's an extensive variable, and we would like to connect Gibbs free energy so this equation connects the enthalpy and entropy with the Gibbs free energy. Now we understood how to calculate the change in entropy and the change in enthalpy in second law and first law respectively. Okay, so now we would like to combine these two concepts of change in enthalpy and the change in entropy, and combine those two things to get a new function which we'll call the delta G. So how do you get the delta G? We start differentiating. Okay, so we differentiate delta G, G, so we get delta G on the left hand side. We differentiate H, we get a delta H. With the product rule, we differentiate Ts, we get a T delta S and S delta T. Okay. Now for a reversible isothermal process, this delta T will now become 0. So when this is then this whole term becomes 0, we are left with this equation, which is delta G is equal to delta H minus T delta S. This is a very famous equation. Like we'll be using this for understanding chemistry in general. This is such a powerful equation because we are connecting enthalpy change and entropy change in an isothermal process, and we are trying to see how the free energy, how the available energy of the reaction is changing. Now why this available energy is important? Because this available energy will give us an estimate about the spontaneity of the reaction. Now we have understood that, okay, reaction spontaneity was understood by delta S, right? And delta H was giving the enthalpy of the reaction. Now delta G will tell us whether a reaction will actually happen or not. So the delta G will give you the amount of energy exchange before and after the reaction. Now if the reaction, the delta G of the reaction is negative, that means the reaction is when things happen. So okay, so for example, if you have a reaction which is going from A to B, and A is the amount, so for A the amount of energy in those reactants is something in here. So this is an energy profile diagram in which we are plotting energy with the extent of the reaction. So say you have some reactants in which they have some kind of energy. Okay, now after the reaction is complete, when this A changes to B, you get the products, and then you have the final products, and then the products have a certain amount of energy in them. Now what the Gibbs free energy will tell you that whether the reaction will be spontaneous or not. Okay, so if the delta G of this reaction decreases, like if the energy decreases from the reactants to products, what kind of energy? The Gibbs free energy. So this is the amount of energy that we are talking about. Okay, so this is the energy. So if the Gibbs free energy decreases, that means if the delta G becomes 0, the G of final, the G of product minus the G of reactants, the initial, becomes less than 0, then the reaction is spontaneous. That means then the reaction will happen spontaneously. Okay, this is very simple concept. Okay, so for a process in which delta G is greater than 0, that process is not spontaneous. Absolutely simple idea, but absolutely critical. Okay, So now when we know that how the delta G is getting, the sign of delta G will actually tell us about the spontaneity of the reaction. Now let's try to see some kinds of examples of reactions that will combine the two concepts of the delta H and the delta S. So the delta H, as we have seen, that can be positive or negative, like it is positive for an endothermic and a negative for an exothermic case, and so for delta S. Okay. Now let's suppose that there is a reaction that is happening and which is exothermic in nature. So the delta H is negative. Okay, the delta H is negative. Exothermic heat is being released. Okay. Now, and if the delta S, like the entropy change of that reaction, is positive, that means this equation, this whole thing, so this delta H is a negative quantity and delta S is a positive quantity. So the negative of T delta S is also a negative quantity. So this is a negative quantity, this is a negative quantity, both only give you a negative value. So the delta G for this type of reaction in which delta H is negative and delta S is positive is always negative no matter what temperature. Right? So this kind of reaction will give you a negative delta G value at all temperatures. That means this type of reaction will be spontaneous at all temperatures, right? Just the reverse of this, if you make the delta H positive and the delta S negative, then automatically this part becomes positive and this part also becomes positive. Both these things becomes positive, and there is no way that delta G can then become negative. So for that kind of a reaction in which the delta H and the delta S are both positive, you will always have a delta G of positive, which says or which tells you that that reaction is not spontaneous, okay, at any temperature. Okay, now that we have seen these two extreme kinds of cases, now let's see some cases in which we have a kind of a play of the temperatures. Like in these two cases, temperature did not have a critical role to play. Like in this temperature, whatever the temperature is, the delta G is always negative. In here, whatever the temperature is, delta G is always positive. So temperature is not playing a part. But in here, if you see, the delta H is, if the delta H is a negative number, exothermic, and if the delta S is also a negative number, so in such a case, what is going to happen? So you see that delta H is negative. Okay, now we want to get this whole thing as negative, the delta G as negative, right? So, but now you see the delta S is a negative number, so the negative of T delta S becomes a positive number. So whatever you do, you have to keep in mind that this delta H should be more negative than the product of T and S. Okay, how are you going to reach that? You decrease the temperature. Okay, you decrease the temperature. So when you decrease the temperature, this whole thing tends to become more negative, right? And when this whole thing tends to become more negative, that means it is becoming more and more spontaneous. Therefore, for an exothermic process, whenever you have a delta S of negative, the reaction will become more spontaneous when you are decreasing the temperatures. Okay? All right. Now, for a negative reaction, if the delta is positive, then at all the temperatures this thing is going to be spontaneous. But when you decrease the temperature, this whole thing further decreases, right? So for an exothermic reaction is favored at lower temperatures. Why? Because this thing is positive, this thing is negative, and you want to remove this thing to count for like less and less negative values, right? So this delta S being a negative number here, in this case, if you lower the temperature, this whole thing becomes more negative. So in this case, when you decrease the temperature, the reaction becomes more spontaneous. Okay. Now in this case, if you lower the temperature, what is going to happen? If you lower the temperature, this whole thing becomes less negative, right? So in this case, if you lower the temperature, it won't make the delta G more negative. But whatever the case be, this whole thing, the net value of delta G is always negative, okay, in this case. So temperature changes, increasing or decreasing, won't be able to make this a non-spontaneous process. But in here, temperature has the capability of making, if you have a lower temperature, there is a chance that the delta G becomes a net negative value and the reaction becomes spontaneous. Okay, so let's look at the last case in which the delta H is positive, which is an endothermic case in which you have a delta S of positive. In similar way, in here the delta H is a positive number. Okay? In here the delta H is a positive number. Now you want to get a delta G of negative. Now the delta S in here is negative. So the negative of T delta S, this quantity is becoming more negative at higher temperature. So if you increase the temperature in here, delta G, it starts to get more and more negative values, right? So in an endothermic process, when you increase the temperature, the reaction will get more and more negative delta G values, and thereby in an endothermic reaction, when you have a positive increase in the entropy, if you increase the temperature, you will start getting more negative delta G values, thereby making the reaction more spontaneous. Okay? All right. So this is the general idea about like delta G, that if it's negative, it's making that means that the reaction is spontaneous. You're decreasing the free energy, the free available energy. Okay. Now, if you do not have the value of delta H and delta S, and then you are trying to find out what's the value of the delta G, so what are you going to do? So if you're trying to find out the delta G for any reaction, right, what you do is a similar process that we did for the enthalpy, right? So Vi is a stoichiometric coefficient, and delta H of Gi, that means this is the heat, the Gibbs free energy of formation of I. So you multiply all the stoichiometric coefficients with the delta Gibbs free of energy of those particular products, and then do a sum, and then you do the same thing for the reactants, right? So you have to find out the Gibbs free energy of formations of the elements. Now, the delta G, or the Gibbs free energy of an element in its reference state is 0. Okay, it is a concept similar to what we were studying in the enthalpy. So the enthalpy of formation of any elements in its reference state was assumed to be 0. In this case, similarly, the delta G of formation of any element in its reference state will automatically become 0, right? So in here, this is how we represent the standard delta G of formation, the standard being represented by this symbol, right? And what's a standard element? Like any kind of like pure crystalline solid will be a standard state. Any kind of pure liquid will be in its standard state. Pure gas will be in its standard state. Okay, so we know how to get to the delta G of a reaction, and then comment upon the spontaneity of the reaction by calculating the delta G by two ways, like directly from delta H and delta S, and by getting the delta G of formation of the individual elements. Okay, so this brings us to the end of the delta G and the Gibbs free energy formation, and we'll be discussing further on how we apply the delta G spontaneity and things like that to explain different stable states, metastability and things like that. But for now, let's finish the delta Gibbs free energy on this, and we'll see other important concepts in chemistry further.